Welcome back to another episode of Syntalks, a podcast which explores the field of synthetic biology. This student-run podcast is organized by the iGEM Toronto team, an undergraduate research team hosted at the University of Toronto that focuses on scientific research in the field of synthetic biology. I am Hannah, the host of today's episode. I'm joined here today with our wonderful guest, Ruhi Choudhary, a third-year PhD student working in U of T's Metabolic Systems Engineering Laboratory. Ruhi, welcome to the show.
Thank you so much for having me.
So, as far as your project goes, we know that it has something to do with the genetic engineering of probiotic bacteria, right, for therapeutic applications?
Yeah.
Would you mind explaining a little more about yourself and your work in the lab?
Sure. So what I essentially do is that I work on engineering probiotics. So we know that probiotics provide some benefits. However, the effectiveness of probiotics is still a topic of debate. So what I do is that I engineer probiotics and impart some diagnostic and therapeutic functionalities to them so that they can act as like living health monitors inside the gut, so that they can detect the disease phenotype and respond accordingly.
Right. So is this something that would have to be hypothetically ingested by a patient, or is it already, are these probiotics already inherent in the gut of the individual?
So it would have to be ingested by them. So, but these probiotics are already ingested by people. You already take them; they're available off the shelf. Lactobacillus is a very common one. It's in yogurt. The advantage of these probiotics is that most of them already exist in the gut. But yes, when we engineer it, and we call them smart probiotics, which is the term that's used these days in the field, you would have to take them orally.
Okay.
Yeah.
Okay. How did this idea occur to you?
So if I have to be honest, I did not come up with the initial idea.
Okay.
So I started working in this in synthetic biology, in industrial biotechnology to be exact. I was engineering E. coli to make biofuels. It was another PhD student's project, and I was an undergrad. But my supervisor knew that I wanted to broaden my horizons and work in a health-related area. So when it was time for me to graduate and apply for grad school in his lab, somehow the stars aligned, and my supervisor got a grant for this project, and kindly enough he thought of me, and I was finally doing what I always wanted to do, which is to use synthetic biology to build better medicines.
Right. So speaking of synthetic biology, actually, there are many definitions floating around. I don't think people have really settled on one exact definition of synthetic biology. So how would you personally define synthetic biology? What is synthetic biology?
That's the $1 million question. It's so interesting. It has been around for a while, and still there's no one universal definition. There are a lot of definitions out there, but I think it all boils down to this common theme. The core lies in the fact that it's the construction of artificial biological systems. So those systems or devices can range from novel enzymes to genetic circuits. So how can we manufacture something unique and useful from biological parts that are already available to us? How can we reprogram existing systems to be better? What new tools do we need to design quicker and smoother assembly of genetic parts? How do we integrate automation and high throughput technologies with synthetic biology? So it's an exciting area because it combines principles of systems biology, engineering, analytical chemistry, which also really blowing up the scope for what can be done in this space.
Right. So I guess going back to your project then, what sort of applications do you see? Because you said therapeutic and treating diseases, but are there specific diseases that you have in mind when you're working in this project, or is it more just a general tool?
So this relates to actually microbiome, the gut microbiome, which is a very attractive field today. A lot of research has shown gut microbiomes linked to diabetes, Alzheimer's, depression, cardiovascular disorders, arthritis. So basically everything that you can think of is somehow related to the gut microbiome. It's only recently that we have understood its importance. So what I specifically do is that I'm targeting disease of the gut microbiome, Crohn's disease in particular. Crohn's disease basically leads to, it's a chronic disorder in which there's inflammation of the gut. And what I'm trying to do is I'm trying to engineer a probiotic so that it can detect and inflammation signal and then produce anti-inflammatory molecules that would interact with the receptors in the gut and then fix the immune cycle.
Right.
Yeah.
Oh, that's really interesting.
Yeah.
Okay. So on the road so far, are there any hurdles that you've encountered, whether it be personal, technical, that sort of thing?
Yes, I think the biggest, there are many. When you're a PhD student, there are some hurdles that you encounter as a PhD student. But I think specific to my project, the biggest one is that the microbiome studies is a new field. It's also very complex. So biology is itself a black box. And then microbiome is essentially a bigger black box. You have a very dense system of hundreds of communities interacting with each other and with the host as well. We're still in the process of coming up with like a geographical map of the gut microbiome. And we also have to consider like the metabolic and spatial temporal interactions that occur. So we're making great strides, but we're not quite there yet. And as a result, we're working with limited information on something that we don't completely understand. So to be specific, we struggled for the longest time to come up with an assay or like a detection method for the molecule we are trying to produce. It is a collaborative effort between us engineers and immunologists and pathologists in different departments at U of T. But you can imagine how challenging it is to produce something when you don't have a confident metric to detect or quantify it. So it's very limiting too, because your future design decisions depend on how much of that molecule is being produced, if any at all. Fortunately, recently our collaborators have seemed to figure that part out, and but it was definitely a huge hurdle for the first year and a half in the project. We were like going in blind, essentially.
Right.
Yeah.
So speaking of hurdles,
yeah,
there is currently a lot of controversy surrounding GMOs among the public. And especially, this being a GMO that would be ingested by an individual, I feel like that would even cause more fear, right, than you would typically encounter. So I'm wondering, as a scientist working on this project, what are some of the most significant or absurd concerns about GMOs that you've been confronted with, and what is your role in curbing these concerns? How do you kind of go about doing that?
Yeah. So this is a combination of ignorance, fear, and fake news.
Right.
The problem is that there is a big gap between scientists and the public in terms of how we communicate.
Yeah.
Of course, there's like a knowledge gap, but that isn't the issue here. We read and write research articles that are filled with jargon and complicated language and large data sets. Non-scientists aren't going to read that. Even scientists who don't work with GMOs are not going to read that research. And public relies on the news. What we need are better technical and scientific writers who are able to accurately translate that information in a very simplistic manner so that common people can understand it. And today, science plays a very important role in public policy and decision making, what we're seeing with climate change, for example. So we need scientists to come up with a better way to translate that knowledge. We're all taught to do this in our communication classes. In undergrad, but we don't implement it in real life. We all have those exercises in which we have to stand up in front of a class and they tell us that okay, just explain your research like you're explaining it to a 5-year-old, and we have to do that, but we're not doing that in the real world, which is what we have to do. So I know so many people, so many friends, family members, fellow engineers who are scared of GMOs. And they're intelligent, but they don't understand the specifics of genetics and biology. So they get carried away by the latest fad, which is organics. Everything has to be organic and natural. They don't really understand what it means, but that's saying you associate the word organic and natural in like a positive way, and anything that's engineered or you say artificial is bad.
Exactly.
So it's just like playing on people's bias, even though there's like no substance to where it's coming from. So it can be very frustrating, but I do think that the scientific community needs to do more. I think both sides have to make an effort. But I think we can do more. I don't think we are doing enough. I think we need to focus on research, sure, but we also need to focus on how we market that research.
That's actually sort of interesting, because I've read, I don't remember where, but someone saying that, an academic paper that's inaccessible to the public is a poorly written one. People kind of emphasize the importance of being super technical and so far removed from being from the public, but
Yeah.
like you were saying, it totally creates these barriers.
I agree.
Yeah.
Like all these journals, they have these certain standards. Our papers are reviewed by other scientists in the field.
Right.
That is fine, but you're just getting a publication then.
Yeah.
And that's not the
Exactly.
point of science. The point of science is not publication. The point of science is actually making a difference. And you can have amazing articles out there which sound very intelligent, but if you're unable to implement those in the real world, then what are you doing here?
Right. Yeah.
Yeah.
So then, just to go on a different track, you also mentioned that you do some community modeling.
Yeah.
What exactly is that?
So communities. So in the real world, in nature, you will not find like it's different. You will not find bacteria like just E. coli existing alone. You will find them in communities. You won't find a homogeneous population. It will be like mixed. So communities, they play a very important role. You find communities in our gut, like hundreds of communities are in the human body itself. And also in the environment, when you're looking at like bioremediation, for example, you will deal with communities. So community modeling is mathematical modeling of the behavior of different bacterial populations. So you can study what happens if they exchange metabolites, or if they're sharing common food source, or if they occupy the same space, or a combination of these things. Now we do have to study the existing systems to see how they work and how we can improve them, which also brings us to engineering communities, which is what we call like microbiome engineering, essentially. Right. So what I do is that I study the effects of different genetic circuits in a community setting to study the population patterns that emerge and what parameters play a role in that. So, for example, if I can figure out what parameters are important in maybe increasing the sustainability of my engineered strain in a microbiome, I can implement that experimentally and then test out that hypothesis.
Right. Yeah. Well, that's all the time we have for today and all the questions we have for today. Thank you so much for joining us. We really appreciate the time that you took out to come speak with us. And
thank you for
good luck
having
for
me.
your work.
Thank you.
Until next time, Syntalks listeners.